Thank you for reminding me.
Yep.
So the letters are different in those because we're talking about different types of objects, but we're still talking about our approximations, our critical values to give us how confident we are, and our standard error to account for how much variance there is in the actual data. So our amount of error is going to depend on, one, our confidence level, and two, how varied the data actually is. So that's why our margin of error has to take into account both the critical value and the standard error. Now, how many of these things do we know? Hopefully we know a lot of them. We know the sample mean. What's the sample mean?
3.7.
3.7. We're told the sample standard deviation, 0.3. We know the sample size, and that sample size is that minimum sample size that we need to be able to have the normally distributed data without being told our original data was normal. So good thing that's 30. If it was any less than 30, we'd have to be told that the original data is normally distributed. Now we could skip over that t for a second. We'll get to that. We have enough information to find our standard error divided by the square root of 30. So we could find that while we're doing things that we know. What's 0.03 divided by the square root of 30?
0.0548.
0.0548 seems reasonable. We just need that critical value. Well, lucky for us, we've got a table of critical values, right? Yay. Oh, that's hard to read that way. We want a critical value for a 95%. We talked about reading these yesterday. They're a little bit hard to read because of the way they give those keys up on top. My suggestion was to focus on the tail size, right?
Right.
So our one tail size in a 95%, our one tail size is 2.5%. Or two tails are 0.05. That's fine too. This 0.975 is that cumulative. So that should be from our level all the way down. So if our 0.025 is there, the 0.975 is the cumulative below it. I don't like that one, but it's a common one to see. But I think focusing on those tails is going to be the easiest way to read it. I don't know about the one in your textbook, but this one's nice. It has the confidence levels at the bottom.
Yeah.
It's like, it knows that this is a, bear of a thing to do.
Yeah.
Now, you might notice also at the bottom, it lists those z-scores. That 1.96 is what we associate with a 95%. But what this chart is doing is, again, giving us a little bit more flex, a little bit larger values for handling our small sample sizes and our the fact that we used sigma instead of, well, S instead of sigma.
Yeah, the text chart ends at the Z line.
Yeah, which is normal. This one added that, which I thought was kind of cool, but I get to cheat, I guess. So which one of these that we use depends on what our sample size is. So we have to go over here and look at our sample sizes. But as we talked about yesterday, remember this chart in general, T-score charts, and your book is no exception, they express themselves in terms of degrees of freedom as opposed to sample size. What was the difference between sample size and degrees of freedom?
1.
Yeah, difference is 1 value. Degrees of freedom are 1 less than your sample size. And we talked about that a little bit yesterday. We talked about that a little bit when we talked about finding the standard deviation, dividing by that n-1. So instead of looking at 30, we're going to look for 29. Now, you might notice after a while the chart starts to get bigger, as does the one in your textbook. After a while, the difference of one sample of 1 degree of freedom doesn't make that much of a difference. But when you're talking about, very small sample sizes of like 4 or 5 or 6, it makes a pretty big difference, that 1 value. So it can be important. So at degrees of freedom of 29, our critical value is that 2.045, which is, again, very close to the 1.96 that we associate, just a little bit bigger to handle our small sample size. So 2.045, we're going to come back up here, 2.045. And it does the same job as our critical value for the binomials. It's just, again, a little bit larger. So now we have all our pieces. Our X bar is the 3.7 plus or minus. We have our t-score, 2.045 times our standard error, 0.0548. If we wanted to find that margin of error separately, just again, because I like to.
That 0.1121.
0.1121. So those are gonna, again, add together. So what, 3.8121?
And 3.5879.
879. Now, while these were percentages, this was 32.3% and 51.7%. What are these? Let's say 3.6 watts and 3.8 what?
There are values for the mean of the population.
What's the unit on it?
Ounces.
Ounces. That 3.7 was ounces. This is just a scale, but this standard error is also ounces. So we're taking that 3.7 ounces, adding and subtracting a little bit more than 2 of our standard errors. Our standard errors were 0.05 of an ounce, give or take. So again, ideally, 9.2 should be very similar to 9.1. The real difference is we're using the standard error formula for continuous data, so we have to remember to use the right standard error value, just like we had to do in 8. The big difference is using the t's instead of the z's. Fair?
So Matt, it's a little off the subject, but I just want to clarify something.
Mhm.
When we do the lab and we have to use continuous data,
Mhm.
can I use scores, percentages on tests? That's
Yeah.
continuous data, right?
Yeah.
Okay.
So let's jump right into another example. Let's be a little more creative here. You are going to launch rockets. Because who doesn't like to launch rockets? Your fuel use should be normally distributed. So you haven't launched these rockets before, but from all your rocket launching experience, which I'm assuming you have a fair amount of, with all your rocket launching experience, you know that the distribution of how much fuel you use for your launch is usually normally distributed. So we get to assume our population of rocket launch fuel usage is normally distributed. The problem with using rocket launches to try to determine how much fuel you're going to use is you usually don't launch a couple hundred or 1,000 rockets, right? You usually only launch a couple. So you get, let's say, 4 test launches. Which isn't very many. And find you use average, again, it's a mean average, of, oh, I don't know, how about 5.1 tons of fuel with a standard deviation of 1.2 tons. Now, 1.2 tons out of 5 tons is a pretty big standard deviation. You notice that, right? So that's a pretty wide range of possible fuel uses. So you want to come up with, how much fuel are you going to put into your budget for all these launches? Well, we could say the average, fuel use is going to be 5.1, but based on only 4 launches, we've got to have we really want an interval around that, right? 5.1, well, how close to 5.1 do we think the true average is? Well, that's what our confidence intervals are for, right? So what do we think the true average is? So I'm going to go back up here. This is continuous data. We're talking about averages we're talking about fuel usage, so it's not yeses or nos. So we're in that continuous variable, or yeah, continuously distributed data column there. So that means we need to find or make sure we identify our X bar, our standard deviation, our sample size, our critical value, which is going to be, again, a t. And from those, we should be able to calculate our standard error and then calculate our confidence interval. That's our point estimate plus or minus our, let me put that margin over it. So that's the plan. Questions about that plan? Trying to strip it down at this point. Now, sometimes they might try to hide some of this information in a problem, but they won't try too hard to hide it. This particular problem, what's our X bar?
$1.2. Oh, no, not our X bar. Our X bar is, yeah, no, it's down.
5.1.
5.1.
Yeah. 5.
What's our S, our sample standard deviation?
1.2.
That's the 1.2. What's our sample size?
4.
4. And we might take a moment to say, okay, what does that mean our degrees of freedom is?
3.
3.
Which is 1.9092.
Well, for what confidence level?
Oh, for 95, I just assumed if they didn't tell us that it would be 95%.
Okay, they didn't tell us, so we're going to assume a confidence level of 95%. So 95% at degrees of freedom of 3. Go to our nice little chart.
3.18.
Degrees of freedom 3.
3.18.
Here's, we get a nice 3.18. We have to be careful of overreading that. It is our tail size we're focused on. Now 3.18, that's a lot. That's giving us a lot of room. Well, we only have a sample size of 4. We need room to make sure we're going to be okay here. Usually with a sample size of 4, we couldn't even do any of this except that we have reason to believe the population's normally distributed. So, you know, this thing is barely trying to work. So giving it that extra space, not a bad idea. How do we calculate standard error?
The standard deviation divided by the square root of n. 0.6.
So then we put all that together into our confidence interval. 5.1 plus or minus. Margin of error is our critical value times our standard error.
Is 1.9092.
1.9092.
Yeah.
That seems reasonable. And again, we didn't necessarily have to calculate that margin of error separately. I keep telling you, I think it's a good habit, but people often ignore what I think is good.
Mhm.
So, what's our high end of an average?
7.009.
7.009. What's our low end as an average?
3.1908.
3.1908. So what do we think the true average is? The true average is somewhere between, I'm going to say 3.2 tons and 7 tons. Just to arbitrarily round. So if you're going to try to budget as we use this, rocket, how many tons should we budget for on average? We'd like to budget for the 7 tons, just to make sure. The budget office would like us to budget at the 3.2 tons because they're like that, and we argue between ourselves. Ideally, as we do more launches, we'll get more data, right? And we can redo this every time we do a launch. You'll get more and more accurate every time we launch, because every time we launch one, ideally, these 2 values should become more accurate. And every time we launch, that critical value will get smaller because our degrees of freedom will increase. We'll move down this chart as we get more and more samples. How do we feel about that example? Okay. A different rocket design is meant to save fuel. It does, let's say 8 test launches using 4.9 tons of fuel on average, with a standard deviation of 1.5. No, let's not even make it 1.5. Let's make it 1.1 tons. Is the new rocket better? Now I'm going to add a little language here to a statistically significant degree. You might, depending on what kind of things you listen to in your daily lives, you might have heard people say, is it statistically significant, or it's not, or is or isn't statistically significant? What does statistically significant mean? We're going to talk about that here. So on the face of it, this other rocket design used less fuel on average in more tests with a smaller standard deviation. So if we just look at those point estimates, it used less fuel in a tighter range. So it looks like it's better, right? But is it possible that it just had a good test day and the other one didn't? Well, of course that's possible. How possible is that? Well, we are actually taking into account how possible that is when we find confidence intervals. Because also this 5.1 could have been a good day, could have been a bad day. We don't know. That's why we built a confidence interval, right? And said, instead of saying it's around 5.1, we said it's between 3.2 and 7. A fairly big range. If we want to see if this rocket design has shown itself to be better in a statistically significant way, we'd have to show that its confidence interval is outside of this thing's range. And we already know it's not, right? This thing could be as good as 3.2, as far as we know. And this thing could be as bad as 4.9. Fair? So already, it's not necessarily better. Fair? Let's go a little crazy here then. Let's say this new engine had an average of 2.4 tons of fuel in its use. Okay, wow, that looks a lot better, right? That is lower than our lowest, right? So again, is this new rocket design now better to a statistically significant degree? We still don't know. Because again, this 2.4 is a point estimate, right? It should have an interval around it, a high and a low. If its high of its estimate is more than our 3.2, it's very possible that it's actually worse. So find the corresponding 95% confidence interval for the new rocket with the 2.4 and see if those confidence intervals overlap. If they overlap, we have not shown that this rocket is necessarily better.
Okay, you're not going to like this question,
I know I'm not going to like it.
but is there a calculator tool?
Not going to answer that question.
I just wanted to double check.
But I will tell you, if there is one, guess where you'd find it?
Under tests, but
In the chapter in your textbook.
oh, okay. I didn't think they gave a lot of calculator stuff like that. Okay, I'll look.
standard error is. Oh, okay. What's it got to be? Somewhere around 0.3.
0.3889.
I got 3.1. Oh, not, never mind. No,
You got that after you multiply?
I was looking at the standard error. I got 3.1.
1.1 divided by a little bit less than 3 should be 0.3, 0.4-ish. So
Oh, I multiplied it.
is having those approximations seem really handy? You know, it's a pretty gross approximation. The idea that this is, you know, somewhere around 3, because square root of 9 would be 3, right? Divided by 1.1, 3 divided by 1 should be, you know, 0.3, 0.4. So if you do something wrong, you can go, yeah, that can't be right. So it's a good habit to be in, kind of come up with those approximations so you can argue with your calculator. I can't tell you how many students have gone, yeah, but that's what the calculator says. The calculator says the orange weighs 5 tons. Yeah, calculator says the orange weighs 5 tons. All right, put it on the quiz. Go for it. I don't care. I've had that argument with a student that their orange weighed, actually it was like 2.8 tons. But I'm like, that's crazy. You know, they were like, this is what the calculator says. All right, fine. I tried. Anybody got a nice margin of error there? Should be somewhere around almost 1.
Point 9197.
Yes.
9197. So that's pretty tight. That's between, no, not 2. That's, ooh, this is going to be tight. That's an upper of 3 point what?
3197.
3197 and a low of
1.4803.
Yeah. Yep.
So we are 95% confident that this rocket was somewhere in that range, and we are 95% confident that the other rocket was in this range. Is it possible that the second rocket is worse? It's possible. Now, it is easy for us to emotionally discount that, but that's because, well, we think it should be somewhere more towards the middle of that interval, but we have no reason to believe that. Fair? Technically, like emotionally, we totally do. Because emotionally, we like our center, right? Because that's the data we found. But within our 95% confidence level, it is just as likely that it is 3.2 as anything else in that interval. Fair?
Is it because they overlap then?
And because they overlap even a little tiny bit, 1.5 all the way up to the 3.3, and the other one goes 3.2 all the way up to 7. Have they shown that this other rocket is statistically significantly better? No, they haven't. If they think it is better, and I would look at this and say, gosh, it's probably better, but you haven't shown it, and the burden of proof was on you to show it. And so I'm not going to spend, $4 billion retooling my factories to use your rocket design because it might not be better. So what is this other company who made the new rocket design going to go do? Ideally, they'll do more test launches. Because if they do more test launches, this interval is going to shrink, right? Now, it might shrink towards that 3.3, as far as we know. Again, the emotional assumption that, oh, it'll shrink closer and closer to that 2.4 assumes that 2.4 is right. Is that 2.4 right? No, it's our estimate. Fair? It could shrink down closer and closer and closer to that 3.3, sorry, while the other rocket shrinks closer and closer to the 3.2, and the first rocket could be better. Fair? That's why we say we have, in a very technical way, we have no evidence to support that the green rocket is better than the blue rocket. We have zero evidence, according to this information, that the green rocket is better. Emotionally, that's hard to say, looking at the data, but that's why we have statisticians controlling our budgets. Because gosh, emotionally, you want to say the green one's probably better, and it might be better. It's got a good chance. Go do some more testing and find real information. Find me a better argument that it is, but here I'm going to give you a couple, $100,000 to keep doing tests to see if it's better, because, this data does kind of have potential that the green one's better. But we have no information that it actually is. Fair? The cold, heartless statistician. Questions?
I think this is my favorite lesson because it's really interesting to see how.
And it's extremely practical. I mean,
Yeah,
this is why we kind of end with this, because this is what people actually go out and do. For example, oops. Yeah. Jim's got pigs. Jim's pigs weigh an average how much do pigs weigh? Pigs weigh a lot, right? How about, anybody know how much pigs weigh? Why do I think Andrew knows how much pigs weigh? I don't know.
I don't.
Okay. How about an average of 352 pounds? There's got to be a type of pig out there somewhere that weighs about that much. Fair? So Jim's pigs weigh an average of that much. We do need...
It's called a boar.
It's called boar at that point. Well, aren't boars the male pigs? Was that hog? I don't know.
This could be a mama.
These are Jim's pigs. Jim's pigs weigh an average of that. We do need a standard deviation of, I imagine pigs are pretty varied. 34 pounds. Wow. That's Jim's pigs. John's pigs, Jim and John. I had cousins, they were brothers named Jim and John. It was always just weird. Could not have been more creative. Weigh between, let's say, 34, three of those is about 100. Ooh, let's go between 194 pounds and 411 pounds. Are Jim's bigger than John's? Now, we need some information here. How many are Jim's, I'm going to say Jim's type of pigs bigger than John's type? So we're not looking really just at their pigs, at their type of pigs. So how many pigs does, Jim have? Well, I don't know either. Don't look at me.
Yeah, don't we just add the number in?
How about Jim has 40 pigs?
Okay, whatever he has 40.
Some number of pigs. And John has, how many pigs does John have? John only has 12 pigs. Clearly, John's not as serious about this. He doesn't know his mean. He doesn't know his standard deviation. And he's only got 12 pigs, right? Jim's more serious. He's got more compelling data and more pigs. Fair? So we want to find, based on these samples of Jim's 40 pigs and John's 12 different type of pigs, we want to find an interval for both of these on what their average size is. Now, this isn't a medical issue, so 99% confidence is not necessary. I'm not even sure 95% confidence is necessary for pig weight. Do you? How about 70%? So I want to find a 70% confidence interval for both Jim and John's, Jim's and John's types of pigs. In terms of weight. That seem reasonable so far? All right. Do that and see what happens. In my head, when Jim and John are arguing about their pigs, it's in a thick Tennessee accent, and I don't know why. Is that a personal bias about? I know people in Oregon who raise pigs, and it's just I should ask them how much their pigs weigh. But for some reason, it's a Tennessee accent in my head. So what's the problem with John's data?
Let's see.
His sample size is too small if it's not normally distributed.
I presume pig weight is pretty normally distributed. So let's give Jim that assumption. But that is the first good thing to notice. Jim's sample size is small, so or John's sample size is small, so we're going to have to presume normally distributed data. So let's put that as a note. We're going to assume normally distributed pig weight. And kind of, you know, based on what Kim was saying, this is a really powerful tool to use. And it really, if data is anywhere near normal, we usually say, okay, it's probably normal enough. It doesn't need to be all that normal for this to work. You know, if it's, you know, crazy, then it's not going to work. But if it's, you know, a little bit left skewed, a little bit right skewed, I imagine pig weight's probably a little bit on the right skewed side, but a little bit of skew doesn't mess it up all that much at all. So if it's fairly normal-ish, it's usually quite sufficient. So I don't think that's a dangerous assumption. Anything else disadvantageous about John's data?
You aren't given a mean and a standard deviation.
Yeah.
We're not given any of the information we want.
Yeah.
So what are we going to have to do to figure out what we can try to use as a mean and standard deviation? Particularly a mean. If his pigs are between 190, whoops, I erased that. If they're between 194 and 410, what could we use as a mean if we were trying to be gross about it?
Can we just add them together and divide by 2?
That's a big assumption, right?
Yeah.
But based on the information we have, it's all we got. Fair?
Yep.
So if his pigs go from 194 to 411, assuming that average is in that middle, average is supposed to be a measure of center, so let's add them together. So it's a pretty big assumption, but it's all we got. Fair?
Yeah.
Jim's data is a lot better. We'll see that. But what do you get as our presumptive average for John?
302.5 by added rate.
302.5. That seems reasonable. Okay, the harder one and the more common one to need, because a lot of people know averages, but you know, a lot of people don't find standard deviation because they'll like that. So how are we going to approximate, roughly, grossly approximate standard deviation based on just this range? See if anybody remembers. We've done this trick before, but it's been a while.
Is that way back in the beginning?
Fairly near the beginning, yeah.
Yeah. What was it?
When we first discussed standard deviation. Let me ask it this way. How many pigs should be within one standard deviation of this presumptive mean? What percentage of pigs should be in that range?
8%.
How much?
68% between the two first deviations.
Okay, so 68%, about roughly 70% of them should be within the first two. How many should be, well, yeah, within one standard deviation of the mean? What percentage of the pigs should be within two standard deviations of the mean?
That's way back. 90, what is it?
95.
95%,
Yep.
roughly.
Yep.
How many pigs should be within three?
99.7.
99.7, almost all, right?
Yes.
So if we took this range and divided it into 6 pieces,
Yeah.
1, 2, 3, 4, 5, 6, those 6 pieces would be the size of the standard deviation grossly.
Yeah.
Fair? We've done that, but we haven't done that for weeks.
Right.
So what is that range? That 411 minus 194.
Let's
What, 217?
Yep.
Divide that into 6 pieces for the 3 standard deviations on both sides. We need 6 pieces. And what do we get?
Let's see. 36.17.
36.17. I'm going to go 36.2 because they're pigs. So 36.2. Now, both of those are fairly brutal approximations, but when that's all the data we have, that's what we can do. And do you suspect out there a lot of people aren't going to give you all the data you want? Absolutely. So these are a couple of nice tricks to know, particularly the divide by 6, the range divided by 6 for our standard deviation. It is a fairly gross tool, but since most people don't give us standard deviation, unfortunately, it's a really common tool to need to use. The nice thing is the n we're given directly. Boom, cha-cha. Now, are the t-values for Jim and John going to be the same? They're both 70%. So are those t-values going to be equal?
No, but because you're have different ends.
Right, the t-value is partially dependent on the sample size. So John's sample size of only 12 is going to make his t larger to account for that than Jim's t. So if we go up to our chart here on 70%, 70% has a tail size of 15. And we go down to a degrees of freedom of 11. That gives us a t-value for John of 1.088. 1.088. While Jim, we got to go down to, well, there is no 39, right?
Oh, yeah.
So we're going to just use the 40. And it's 1.050. 1.050. So quite a bit smaller because of the larger sample size. Both of those are fairly small for critical values, but that's because we're only trying to be 70%.
And the books chart does have a 39.
Oh, good. What is it for 39?
It's 1.050.
Oh, okay.
What page is that on?
It's about the second to the last page. It doesn't have a number on it.
Of the whole book, yeah.
Of the whole book.
It's in
Table
your
6. VI.
table Roman 6.
Roman number 6.
So our standard error, 34 divided by the square root of 40 for Jim, and 36.2 divided by the square root of 12 for John.
So Jim's is 5.3759.
5.3 what?
759.
759.
And haven't done.
John's looks like about 9, maybe 10.
See.
10.45.
10 point what?
10.45.
10.45. Good. Then our margins of error should be the t-score times the standard error.
5.647.
1 second here. And you said 5.4?
5.647.
647.
647?
I got 6447.
Oh, that's possible.
5.6447.
Oh, okay.
5.64.
Perfect.
And the other one? 10 point. That's that product. Tell me.
11.3696.
11.37. Again, John's margin of error is much larger. It's almost twice Jim's margin of error. Well, why is that? Because Jim's got a larger sample size is one of the big issues. Also, the standard deviation for John is probably artificially high because we had to do the entire range divided by 6. That usually gives a higher than accurate standard deviation. But again, this is all the information we had, so we had no choice. So the 352 plus or minus 5.64 is like what, 360? 360, where did I get 360? 57.64 on the upper end and 346 and change on the bottom end.
34.36.
For John, 302.5 plus or minus the 11.37 is what, about 313, 314. I'm just approximating here real fast because I know you guys have to go. And what, 290-ish?
Yeah.
So can we definitively say whose pigs are bigger or smaller? Yeah, these intervals do not overlap, right? So are Jim's pigs bigger? No. John's pigs are significantly again, that significantly, we often use that word in conversation, significantly bigger, to mean, to emphasize like significantly bigger. They're a lot bigger. And really what it means is it's significantly to a statistical degree. They're bigger enough on average that they're a different thing. Jim's pigs are different than John's to a statistically significant degree in terms of size.
So you're saying that John's are bigger than?
Sorry, Jim's are bigger.
Oh, okay.
Sorry. My cousin's John was the bigger cousin, so I should have switched them. So I think of John as being the big guy, Jim's being the small guy. That's why you don't pick names from your life. You really don't. So Jim's pigs are a different type of pig than John's pig to a statistically significant degree. Because they don't overlap.
Jim's pigs are significantly bigger, right?
Significantly bigger. Oh, I said, I wrote John, didn't I?
Yeah. Okay, Jim.
No.
Yeah, okay.
Oh, so are Jim's pigs bigger? Yes, Jim's pigs are bigger. I just switched the names completely in my head.
Yeah.
Yes. Jim's pigs are significantly bigger. And, significantly bigger, what is significant? We often think of significantly, it means it's a lot bigger. Well, yeah, it's enough bigger that we can definitely say it's a different population of pig. Questions about any of that? All right, I gotta send you off today. We're over. Not that I mind being over, but Camille, was that better today? Fair.
Yeah, I thought it was helpful.
Okay, work on this. Let me know how it goes. And we'll talk more Monday. I can't come and like last Friday, I think it was great. I came by and we talked. I thought that was nice. I can't do that this week because I have a procedure on my back tomorrow morning. They're gonna stick 4 8-inch needles into my spine tomorrow morning. It's very exciting. So that'll be fun.
Okay.
So I can't be here tomorrow, but I'll see you on Monday. And if something comes up over the weekend, let me know. I'll give some sort of help if I can. Okay?
I had a quick question for you once after, not related to math.
Camille, do you want to go and come back and work on it?
Yeah.
Okay, I'm leaving and I'll come back.
Okay.
Yeah.
Yes, ma'am.
I'm still attempting to try to work ahead. My goal is to have everything done hopefully by Saturday. If I get stuck on stuff and I can't get my test done, I saw you moved it to next Wednesday or Thursday.
Mhm.
If I don't get the test done on Sunday, I will try my best to be functional to take it on Thursday. But if for some reason I'm like looping out of it, what should I do?
There are lots of options. Grades aren't due until Monday.
Okay.
So you could do it, Friday, Saturday, Sunday, even Monday.
Okay. I mean, I'd like to get it done. You guys need to stop. Sorry.
And worst case scenario, we could even do it after that. That's okay. Even worst case scenario, we could even do it after that. We would just have to put in either a placeholder grade or an incomplete.
Okay. I'm really trying to get it done before surgery just because I don't know how things are gonna.
Oh yeah. Well, and it might help to know that there's not going to be anything from chapter 10 on that test.
Okay, so it'll just be 8 and 9 and then whatever else before that we have to build up to.
Right.
Okay. Okay. Yeah, it's more just getting like all the homework. So do I need to do the homeworks for chapter 10 at all or no? Okay, so I'll just work on all the chapter 9 stuff and then review and then I'll just jump into the test.
Yep.
Okay. Is it okay if I do my labs and stuff after that? Because that I might, if I can't get to those, I might, it's all time dependent.
It's fine.
But okay. Sorry, this is such a pain. I was all kind of last minute and unexpected. So
Yeah.
Well, thank you. Is the test unlocked right now? For me to do?
No, but send me a message and I can send you the code that it will ask you for.
Okay, I'll do that right now so I don't forget.
Okay.
All right. Well, thank you so much for
Oh, of
working
course.
with me. It makes this is my last class. I've been having to retake all of my courses in science for this doctorate program I'm applying for because I graduated college in 2009.
Yeah.
And they wanted everything 7 years current. So I already redid like all of my anatomy and physiology and whatever stats class I took back in the day. So anyways, thank you so much. I will send you that message now and try to get this done. Well, have good luck with your punctures. That'll
It should be nothing.
never fun with the,
No.
yeah. All right. Well, thank you.
Sure. And have a good day. And if anything comes up, let me know.
Okay, I will. Thanks.
Bye.